Welcome back, Quant Files, to INST 314, Statistics for Information Science. I'm your host, Sean Jansen, continuing our adventure on this topic of descriptive statistics and charts. And in this last video, I'm very excited to talk to you about presentation quality tables and charts, a topic that's very near and dear to me because all too often in the world around us, we see all sorts of data visualizations and tables that are producing information to help us more easily digest information, but are being portrayed in such a way that make the data misleading and don't do the data justice. This is the reference to where I was talking before about the chainsaw, and it could be dangerous to both you and those around you. If information is not portrayed accurately, then we could be doing a disservice, not just to the data analysis community, but it could have harmful effects on the world around us. So presentation quality material is very important to make sure we get right. All right, now in this little last and final lecture for our descriptive statistics and charts section, we're going to have a little bit more fun, not so much theory and R and other of this crunchy stuff. We're going to look at some of the good, some of the ugly, and everything in between. So we're going to talk a little bit on how to make the presentation quality charts, and I'll point you out to some of the resources that we have in class. So I just want to kind of again bring up this idea that a picture's worth 1,000 words. You've probably heard this 100 times, but it doesn't make it any less true. So the idea came from somebody who said, the drawing shows me at a glance what would be spread over 10 pages in a book. That was supposedly the original source back in 1862. Wow, 1862. Benjamin Disraeli said there are 3 kinds of lies: lies, damn lies, and statistics. Then he says, 9 out of 10 people said that was Mark Twain. Then it says, well, 3 kinds of punchlines: obvious, painfully obvious, and he says, I thought the Twain bit was an added extra layer. What I'm really trying to get at with this particular one here is that Mark Twain and this guy Disraeli, it was trying to say who said it first, and the more to the point that you can use statistics to lie very well. So let's go ahead and take a look at some examples. Here we have a graphic. Should you avoid using misleading data visualizations just to support your argument? There is a large green board portion that says yes, and underneath that yes says 50%, and then a much smaller portion that says answers other than yes, 50%. Curious what's wrong with this one. How about the idea that the percentages are 50-50, but the green has been intentionally made far larger to make it look like it's been disproportionately favored, which is not true. Here's one, a screenshot from Fox Business. I've added the numbers here with the white boxes only to make them more visible because the screenshot really wasn't so clear, but the numbers do match. And in this case, what we have are the small column says about 35%, the tall column is almost 40%, and yet the scale of them are absolutely off. The 40% looks so much larger than the 35. Reason being, they truncated the axes on the y. The y-axis doesn't start till 34%, and that stops at 42, making it look like there's a much larger distinction between these than there actually is. Now, I don't know what they were thinking here at NBC, but this particular graphic is just all sorts of messed up. How concerned are you about the Zika virus? We have tall columns in the not at all, but that's only 13%. And yet our 34 is far smaller, and our 28, which is still pretty large, is almost non-existent. So I think somebody's graphics got a little tinkered with here. This is a fairly well-known image right here that was put forward by Representative Jason Chaffetz of Utah back in 2015 during a congressional hearing when he was talking about Planned Parenthoods and the abortions that they were supposedly providing as it relates to their other services such as cancer screenings and preventative services and things of this nature. And what he was trying to show was this strong relationship that their cancer screenings are going down and their abortions are going up. But look at the counts on some of these things. Look at the slopes that would be here. So the abortions are in the hundreds of thousands, sure, but has a far fewer size effect than the cancer screening ones. So we have to take into consideration, again, scale on some of these things, and it's missing a y-axis. What we also don't know, and could be extremely misleading for a group like this, is that he's taking data from 2006 on the far left and data from 2013 on the far right, but we are not given any plot points for those in between. It very well could be that there were some very tall spikes and valleys. It could also be that they were plateaued. It could also be that maybe cancer screenings were way up, and then in maybe 2013 there was a drop, or similar with things with abortion. So this could be a strong case of cherry picking our data as well as improperly graphing it. Here's one where we have two different graphics. The one on the left is an okay one. The one on the right, not so much. So the one on the left is data using bars, and it shows the average cost of a 30-second Super Bowl commercial. And in 1967, it was about $500,000 per 30 seconds. And by 2010, it was about $3 million for 30 seconds. That's about a six-fold increase that we have there. But if we look at the one on the right, it's supposed to be the exact same idea. Average cost of a 30-second Super Bowl commercial increasing on the y-axis and costing millions. But they're using an idea of circles to show the magnitudes of increase. And if you were to stack beach balls on top of each other, circles stacked on top, you could portray 6 of them stacked up and do a fairly decent job. You'd be wondering why you're using beach balls for that, but that point is really just for this example. But when you're using the circle idea with these beach balls and you are expanding them in size, it is no longer just their height, but their overall volume that's distorting the image of the data being presented. Again, no pie charts. Here's just a silly one that came out a while back that's just talking about some of the ridiculousness of the infographics that we have out there these days and the amount of data that are being put into it that really just is not being useful. And so he says he's seen over 3,000 infographics this week. None of them had anything much more than simple graphs and splashes of color. And most of them had some sort of figure or pie chart that made it look far more complicated than the one that was right there. And then last, he said the number of countries have been in when they saw infographics on their computer screen. So definitely a bit of a cynic, but a fun one at that. So let's talk briefly about presentation quality, or PQ, tables and charts. When I say PQ, I mean a professional, clean way to convey your interpretation. It should be clean. You look at it, you should be able to understand what's there right away. And you can have color and flash, but it doesn't have to be. It can be very plain. The idea is that it looks professional. In fact, if you have too many colors and bells and whistles and trinkets, it can actually draw away from the message that you're trying to portray. So keep some of those in mind. Now, PQ tables and charts are going to be the class standard. If I ask you to produce a table or a chart, I mean produce a presentation quality table or chart, unless I specifically mention. There's going to be instances that we're going to use certain plots in R, and they just don't conform very well to be making PQ from their default settings. So keep in mind, you're going to be doing PQ all the time. There is a file in the Elms directories called Making PQ from R output, and it's a step-by-step that shows from when you generate the output in R, you can copy it and paste it into Excel, and that's how you can go ahead and make a table. And once you have the table, you can go ahead and make a chart and things like that. We're going to be using R and Excel in this course, but if you want to be able to pipe the data out to another external source to help make your graphics and whatnot, we can talk about that as you go. Come ask me about those things. And then we're going to have many other options outside of class that you can be doing these that I just mentioned, Tableau, Python, things like that. So when you want to go ahead and make good PQ tables in R, the general rules of thumb is that when you do it in R, the nice thing is that it's reproducible and customizable. Tons of code to do things like that. But that, again, is the bad side. It's going to take you some time to go out there and find the code, to learn how to do it, to find the packages, and do that. Another downside is we're not taking time in class to show how to do it in R. There are enough tools. You can do it in Microsoft Word. You can do it in Excel. So we don't have to spend much time learning all of the different code to help you do that. It can be also integrated to work with HTML, LaTeX, PDF, things like this. And I'm providing you several different links here to different packages people have put out to help them make different tables and codes in class. So feel free to dive into that if you like. So when we are reporting our values here, this is not just in tables, but this also applies to our words and the Word documents and things like that. We're going to be using the APA, American Psychological Association's citation for statistics. When we get into some of our future lectures, like the different inferential statistics, I will be telling you during those lecture slides what the APA format looks like. However, there are also help files in the ELMS directories. I believe they're under the Other Resources folder that you can go ahead and look at some of these citation options and the different examples that they have. So let's just briefly here take a walk through our gallery of goodness, some PQ tables and charts that do the job right. So here we have a chart on the left and a table on the right that look good. The chart is clear, it's not cluttered. When we have percent signs on top of the bars, and when you have those, you don't need the y-axis. It's pretty clear how large each of those columns are. The title of the chart and the axis labels, they are large, clear, and easy to read. And there's a sample size that's underneath at 138. That way we've got a reference point when we're looking at those percentages of how many people were actually there. 33% for some of 100 is a lot different than 33% of 10,000 or 100,000. On the right side, we have a summary table that is strong for interval and ratio variables. And so we have a table title, and then we have sort of a subheader system where we have all of the different major summary statistics that we might be asking for, and then their values underneath. Posing this horizontally posing it vertically instead of horizontally is also a useful option. These are a bit more busy, but still PQ. You can look at them and pull out the data that you need. On the left side, we have a more complex table. So it says we have a table title with social capital measures for job searches, which then break it down into 3 columns for neighbors, coworkers, and friends, and then the response options for each group on the rows, followed by total columns for N and percent. Underneath that, we offer the question wording. So if this was part of a survey or other research question report, we're telling you the question that's being offered. It's a little above and beyond for the question component, but still it's PQ because of the way it looks and the ease of getting the information out. Similarly, we can take that same information and put it into a graphical component, and it works because we don't have a large N for these different social capital groups, neighbors, coworkers, and friends. If we had 6, 7, 8 even of these, our x-axis would be getting very long. We'd have tons of little columns for each one, and it might become a bit unwieldy in general. So just for when you're doing this, it's a matter of perspective and practice. So let's go ahead and look at the gallery of shame. All of the graphics and tables you are about to see here are real ones that previous students have done and are anonymized, so we're not going to find out who did them, but we're going to talk about some of the problems that came across them. So on the left side here, someone tried to make a chart about the rates between falling behind in your mortgage and getting evicted. And this is a good start, but there's a lot of gap in the middle. The particular variable that was used here was binary. It was like a yes-no sort of thing, but it was coded as a number. So R saw it as a number, stuck it in here, and then said, well, there's a lot of potential numbers in between. If that number was treated as a category when this happened, then the entire plot type would probably change into something that would be a bit more favorable to it. Likewise, on the right side, we have a table, and it's missing a table title. It has the question, but it's been put up at the top instead of the table title, so it's a lot to read just to get a sense of what's going down below. Then it says, well, there's a strongly disagree, and then 2 response groups, willing or not willing. Okay, but there should be more to it. What other options were there besides strongly disagree? We're also missing the percentages or proportions and what those sum to in terms of totals for both. So much to be improved there. Similarly speaking, these others that were not quite PQ, the one on the left has another problem where they made this one in Excel, but when they dragged across Excel to indicate what values they were going to include in their chart, they left a couple of them open and blank, and so it made blank spaces in the iSchool based on those actions. Similarly, the table that we're looking at for if you're looking for a job, it's not as bad, but we're missing the frequencies. So in this case, it's tough to say it's 100% and almost 70 and 30% split, but of how many? 10, 100, 500, 1,000, etc. We need some more context with the frequencies. So also, just as it's a minor nitpick, that's technically a table, not a figure. So it should be table 1, not fig 1. But this goes ahead and wraps up our talk on presentation quality tables and charts. I look forward to working with you during lab time and future exercises to help you build the skills on making good looking components so people can get the core presentation of your information accurately, correctly, and on the first try.